Now that we've gone ahead and collected our raw data, the next thing you need to do in the RAC section is start to process your data. Typically we do three things on there. The most obvious thing you do is averages and standard deviations. Then you should have some sort of graph, and then you should have some sort of statistical test that you perform on that data. You can do more than that, obviously. Conversions are always a very nice thing to do, but you should certainly have those three elements in there. Now what I've done over here is, on the statistics practice, I've put in a sample set of data here, and I just want to kind of show you quickly how we'll do things. Mostly we're going to use Google Sheets. I don't particularly like this program the best. I think there's better programs. I like using Microsoft Excel myself, but I know that this one was included on your Chromebooks, so that's what we'll do. In this first one here, I have a sample set of data comparing EVS with ecological footprint. I'm just going to go ahead and copy and paste it over here. And the reason I'm going to do that is because I want to also go ahead and organize my data. If you go up here to Data, you select Sort. We don't want to sort the whole sheet. We just want to do the range. I'll click on this, and you can see that it then divided it between the three different types of EVS. Kind of a nicer way to present your data. So the first thing you should really be doing, almost in every paper, is calculating averages and standard deviations. The formula for average, and you always write equals, is average, open parenthesis, and then I'm just going to drag over the data that I want to average. And if I do the same thing for all of them, dragging over different data, I should go ahead and find out what the averages are. Sorry about that, misspelt that. And average for Technocentric is here. Now if you look at those numbers, you can say, well, they all look different. 60, 71, 50, I guess there was a difference because of the environmental value system that you chose. But we need to do more than that. We need to also go ahead and do the standard deviation. And that is the error, the uncertainty. So the formula for standard deviation equals, again, is STDEV, open parenthesis. You drag over your numbers one more time, and then you get the plus or minus error on it. So let's take a look now at what happens when we put that information in there. When we started off here, we thought that the averages were different, but when you consider the plus or minus, maybe they're not really that different. So for example, 60 plus or minus 29 could get you down to 31, and 31 is way lower than 50. And 60 plus or minus, so we add 29, we get up to 89, that includes 71. So when you consider the error bars here, actually, statistically, those averages are the same. In other words, if I sampled more than just these few here, I might have found the averages to be very close. We can show that by doing a graph. Let's go ahead and do it. Now, typically, we never graph raw data. We usually just graph the process data. So I'm just going to choose this right here. You go up to Insert and Chart. It automatically defaulted at the correct graph, which is a bar graph. And the reason why it had to be a bar graph is because the X values here, down here on the horizontal, are alphanumeric. They're not numerical. So I really couldn't do a scatter plot. Now we'd go ahead and fix this up. Let's go to Custom. Let's put a title in here. Titles tend to be long and boring, but I'm just going to put in a short title so you get the idea. We should also go ahead and put in on our horizontal axis, so that was the EVS, and on the vertical axis, that was the ecological footprint, yeah? If there were units, we would put those in there too, but I don't think these really have units. The last thing we need to do to show that these averages really are not statistically different is put in these standard deviations. So I'm going to go back here and click on Edit, go back and do it one more time. Now the problem with using Google Sheets is it doesn't have a lot of good features to doing error bars on it. I think Microsoft Excel is much better. And what's going on here is that this data right now is one series, but we want to put in three different error bars. So we're going to do a little razzle-dazzle on this. If you go down here to where it says Switch Rows and Columns, I'll click on that. And what it does is it breaks it up so I have three different series. Each series just has one data point in it. And I know that because it color-coded it for me. And what I can do now is I can go to Customize, go into the series. You can see now I have 3 different series, and I'm going to add these error bars in there one at a time. So let's do the first one, the blue Anthro. And you go down here where it says error bars, click on that. What type of error bar? Now I know it says standard deviation here, but that's really just a trick. We want to go to constant, and you want to put in the number, and it was what, 29 there? And now it appears up there. Let's go ahead and do the other one. Eco is red. We're going to go back to error bars, back to constant, and this time we want to put in 27. And then we go to our last one, which was the technocentric. Click on that. Error bars, constant, and this time it's 43. And there's our error bars. And now you can clearly see they really overlap here. I'd probably want to remove that 71 here from the values. Now I grant you this is terrible data. Hopefully you'll have much better data than mine. I just made this up. Typically your error bars should be not more than 10% of the average value. Obviously these are terrible, but I just want to demonstrate how we do a bar graph or histogram. The next type of test you can do, or graph you can do, is a Pearson correlation. Typically we know this as a best line fit. I've got here a sample set of data comparing the Human Developmental Index with the gross national product. I'm going to go ahead and drag over the whole thing here, go to Insert Chart again, and this time you can see that it defaulted as a scattergram or scatter plot. And that's because both sets of data were numerical, so I think it did the right thing. Now I can obviously override it over here and pick whatever I want, but I'm going to stick with the scatter plot for now. You can also see, since I dragged over the labels, it already put them in here with a title. I could change that, but I want to be lazy and just move on here. We want to put in the best line fit, and the way you do that is very simple. Click on any point. It comes up over here. There's the series we want to do. We go down here, and sure enough, it says trend line. Let's click on it. It defaulted as a linear. You don't have to do a linear. There's other choices. You can't just arbitrarily choose one of them. You have to have a reason, and you should explain that in a footnote perhaps below. So for example, if I was doing a biological experiment here, I definitely would not choose a linear fit. That really wouldn't make sense. You'd want to talk about limiting factors and so forth, maybe a polynomial fit. But on this one, we'll stick with a linear fit. You don't have to have the values here. It kind of defaulted there. I could remove them if I wanted to. But this is not enough for the Pearson correlation. We need to also show what the equation is. So if you go down to Label, change None to the equation, there it is. And we also want to show the R squared value. Now the R squared value tells you how good a fit it is. If it was number 1, that means a perfect fit. Obviously, this is not a perfect fit. Boy, it really is missing a lot of the points here. Not 1, but 0.159. That's a terrible fit. And you should talk about that in your report. Now, again, I just made up this data. Hopefully, your data will have a much better R squared value than I did. That's a Pearson correlation. But we got to do a statistical test also. Now, there's 2 very good statistical tests people do. One is called the t-test. The other is called the ANOVA. You can decide which one you want to do. A t-test simply compares 2 sets of data to see if they are significantly different. Now I have here 2 sets of data, one from lesser economic developed countries and one from more economically developed, and I'm looking at the GDP. I went ahead already and put the averages and standard deviations here. And the reason I did that is to show you that statistically so far, they're not really different. In other words, if I take 2,789, subtract 1,276, oh, that gets me about 1,500. If I take 1,100 and add it to 600, that would give me 1,700, so these actually would overlap if you graph them. So far, they're not really statistically different. But a t-test here considers more things. It considers what the size of the sample is and how different the sizes are. These are not the same number of data points. It considers the averages and standard deviations. It considers if there are outliers. It considers what the size of the values are. So a lot of different things here. In order to do a t-test, it's very simple. Equals, that's how we always bring up a formula. And the formula for t-test is, surprise, surprise, t-test, open parenthesis. Now we need to enter in 4 things here. The first thing is you drag over the first array of data. There it is, comma. Then we drag over the second set, comma. And now we're going to put in a number 2. And the reason why we do number 2, you can see I wrote it down there, is we are considering both sides, plus or minus, comma, and then 3. Now what is 3? There's a whole bunch of t-tests you can do. 3 means that the data is unpaired. For our purposes, we will always choose number 3. Close parenthesis, and there's my t-test number, 0.00039. Now, we are doing our statistical tests for 95% surety, or what we put down as 0.05. I know that sounds like 5, but it indicates that 95% is what we're looking for. It's very simple. If the number that you get here is less than 0.05, then it is significantly different. And this number is definitely less than 0.05, so we would say that the 2 data sets are different. Okay? And that's kind of what we felt they were. So there was an effect of changing it from LADC to MEDC. If I got a number, say 0.08, that would be greater than 0.05. That would say that statistically, these 2 sets are the same. So to have a good report, we're really looking for a t-test number that would be less than 0.05. Now, 95% surety sounds really good, but actually if I was publishing a paper, it would be rejected. They want you to have greater than 99%. So for example, if I developed a new vaccine for cancer, but I said there's a 5% chance that you'll die from it, I don't think people would take that vaccine. We want to be much more certain than 95%. The other test you can do is the ANOVA. Now, the t-test told us the difference between 2 sets of data. An ANOVA says I'm going to look at multiple sets of data, and I'm simply going to tell you, did changing the variable matter? Here I have 3 sets of data, mortality rates from poor, moderate, and rich countries, and I want to see if changing them matters. Unfortunately, on Google Sheets, unless you have the additional data package, it does not do the ANOVA, but I have an online program here which does. Let's click on it. All we have to do is enter in our data sets. It lets you do up to 5. We've only got 3 here. We certainly want to have more than 2. And all you have to do is just copy and paste the data in there. And then we can go ahead and perform the test. So I'm going to quickly copy and paste the data in there. And then, where's our last set there? Got it. Very simple to do. And then once it, oops, I think I went ahead accidentally and clicked the top there. Oh yeah, we don't want to put that in there, do we? Let's get that set in there. Better. Now you can see it's defaulting at a significance level of 0.05, which is 95% surety. Let's click calculate. And it tells us a whole bunch of mathematical expressions here. We don't need to. Some people like to copy and paste this in their report. You don't have to. Let's look at the bottom here. The p-value we got is 0.00001, which is less, much less than the 0.05. So we would say that the data sets are significantly different, which means that going to the data sets by looking at the amount of wealth the country has, it did make a difference in the mortality rates. Again, the value we're generating is less than 0.05. Hey, by the way, just looking at this ANOVA program, it's kind of nice. It also did all the t-tests here. So not only could we see that the variable mattered, the independent variable as we changed it, but we could see where it mattered. So it compares data set 1 and 2, 1 and 3, 2 and 3. This was not a significant difference, but this one and this one were significant. So that's kind of a nice test. Maybe it does the t-test for you besides doing the ANOVA all at once. The last thing I wanted to show you that people do here, and this is another sort of processing technique, is to look for outliers. We all get values that we look at it and we know, I must have just screwed up somewhere. So I've got a data set here. I've duplicated here because I want to show you the before and after. There's the average and the standard deviation. Again, terrible standard deviation. And we look at that 88 and deep down, you know, that number looks like it was a mistake, doesn't it? What would happen if we took it out as an outlier? But you can't just randomly take out numbers that you don't like. You have to perform a test. So we're going to do the outlier test. I have a link for you here. And if you go back to middle school when you do box and whiskers and you know what quartiles are, that's how you do the test. But this is a very simple program. Again, you can see it's set for a 95% or 0.05 standard. We're going to go ahead and copy and paste in our data. Let's copy that and we'll put it into here. And then we just click on calculate. And sure enough, it says that 88 was a significant outlier. Fantastic. And you would need to have a footnote to say that. So we'll go back here and let's remove it and see what happens now. Wow, not only did the average change, but the standard deviation really got a lot smaller. So this is a nice thing to report, whereas this looks terrible. You can't just remove it. You have to say, I performed the outlier test, and this is what the outlier equation was. So that's basically how you want to proceed here. We want to have, from our raw data table, we will certainly want to do averages and deviations. You should have some sort of graph, and you should also have some sort of statistical test. You don't have to do them all, but I would do at least one to do processing.